Afternoon. For this third video about chemistry, I wanted to just throw in some odds and ends, some extra things that you probably ought to have heard about at some point in your life. And so let's take a look at those now. Right here we can make solutions. A solution is a mixture of two things. It's not making a molecule. There's not a chemical reaction going on here. We're just mixing two things together. And so a classic example would be I could have a solvent, like a cup of hot water, and I could have a solute, like a spoonful of hot cocoa or chocolate or sugar or salt or anything that'll stir into the water. When I stir those together, it's called a solution. So very simple idea, just mixing two things together. It would be possible to get the two separated back out, right? I could either boil off the water and I'd be left with the chocolate. Whatever I need to do, there are ways to separate those. Solubility is how much solute will mix in a given amount of solvent. Misspelled there. You've probably noticed that if you put in 1 spoonful of sugar into water, that mixes very nicely, and 2 might go all right, maybe 3, but at some point the sugar starts falling out of the water and building up on the bottom of the glass of water. It just won't hold anymore. And so this solubility is a measurement of how much solute can I mix into a solvent and still have it suspend in there. Saturated is a term that means it's full. It won't take any more. 100% of the possible solute is in the solvent. So a couple terms, definitions there. I'd like to show you this picture. This again is water. Water is what we call a polar molecule. And when we say it's polar, it's because it's positive on one side and negative on the other side. Now let me show you why it's positive and negative here. Here is the hydrogen atoms are tied on to the oxygen atom here in a covalent bond that we discussed. Since those electrons like to be in the middle of all of that nice positive charge, I've got positive charge here, here, and here. All those nuclei are positive. These electrons like to spend time in the middle here. So instead of the 2 electrons that are going around the hydrogen thing going around, they tend to spend more time on this side. That means that this hydrogen nucleus is poking out of the top of this water molecule, and this one's out the top. So there's a net positive charge on this side of the water molecule. Meanwhile, these 2 extra electrons that snuck in here to the oxygen thing, remember these electrons don't like each other, so they kind of shove all the other electrons around. I get more negative electrons here than normal, so this would be a negative end. Water has a positive charge on one side and a negative charge on the other side, and we say that it is polar. Polar means that if I have a whole bunch of these water molecules, that they will kind of align, that the positive end here will be attracted to the negative end of another water molecule, and so on. And so they kind of chain up. It's not a bond. It's not a chemical reaction or anything. It's just positive negative charge being attracted to one another. But this attraction, these polar molecules lining up like this, is what gives water enough tensile strength so that a little bug could walk across or a leaf could float on the water. They hold together, and they'll hold little things up, or a boat, or whatever. Right here, maybe a boat's not a good example, but you can float a needle on top of water, for example, because there's enough cohesive tension there to kind of hold the water molecules together. Non-polar molecules do not have an orientation. There's not a positive end, negative end, and so you see here some non-polar molecules. Notice how they're just bouncing around random. Not anything special happening there. Polar molecules not bond together, but are attracted to one another. Non-polars do not. That's why oil and water do not mix. And so in the glass here, you see that there's water in the middle and some oil floating on top. It looks like there's a heavier oil that has sunk to the bottom here, and they won't mix. Now, if they were both polar, they could mix. But as it is, this attraction kind of pulls all the water together, and anything that's lighter is going to float on top of that. Anything heavier is going to sink, and so it goes. Here's an interesting little thing. Once in a while you could take this water molecule and everybody's happy, but this hydrogen nucleus over here could go wandering. It could go off on a little trip. And what that leaves behind is this thing. Now remember, the oxygen was number 8, hydrogen's number 1. So I started out with 8 plus 1 plus 1, 10 positive charges and 10 negative charges. If one nucleus, one hydrogen nucleus, the proton there, wanders off, that's one of my positive charges. So now I have 10 negatives and only 9 positive. This is a ion. This is a net negative charge to this thing, and we call it a hydroxide ion. The hydroxide ions are important because they make bases. And here you can see the picture. Here's the hydroxide ion. It is possible for that nucleus, that proton, to come over here and fall under the influence of another water molecule. Remember, this had a negative charge on it, the polar water. So a positive proton here could be attracted to that. This much water plus 1 proton would be called a hydronium ion. It's got a net positive charge. So those are kind of interesting right there. The reason they're interesting is that if you get a whole bunch of hydronium ions together, we call that an acid. Acids are solutions that contain more hydronium ions than hydroxide ions. The resulting electric charge is positive because remember, we've got extra protons built in there. You know that acids taste sour. Lemon juice is a classic example of that. It has citric acid in it, and we certainly know it's sour. There's a kind of paper that we can use, pH paper, and if you dip pH paper into an acid, it turns pink or red, depending on how acidic it is. So acids are an interesting part of chemistry. The warning label that they usually put on acids is pretty telling. It says, watch out, you're going to eat the table, you'll eat your hand here. You do have to be careful with these. Those extra protons there make it not unstable, that's not the right word, but chemically reactive. And they're trying to get back to being a hydrogen, so they will work out deals, and it changes the chemistry of it. Bases here are the opposite of acids. Bases are solutions that have more hydroxide ions than hydronium ions. Electric charge is negative. Bases taste bitter and feel slippery. Soap is a good example of a base. You know that it's slippery. That's why we use it. We let that dirt slip off of us when we wash our hands with soap. Some of you, thanks to your mothers, may know that soap is bitter. So I think you can kind of remember those there. Litmus paper, or pH paper more properly, turns either pale or medium blue in a basic solution, depending on how basic it is. So it's a scale. It's a gradient from very acidic to very basic. And the scale that we use is called the pH scale. You can see here, this is a picture representation of the pH scale. It goes from 0 up to 14, and 7 right in the middle is neutral. So perfectly pure water is neutral. It's not an acid, it's not a base, perfectly safe, everything. But as you go this way, as you go down in pH, you get more and more acidic. Battery acid here is a strong acid, right? You don't want to get that on you. pH of 1. Lemon juice is not as acidic, but it's pretty sour, and it's pretty unpleasant to drink large quantities of it. So that's about a 2. Vinegar's about a 3. Soda here, that'd be Coke, and the soft drinks that's acidic. The damage that it does to your teeth, some of it's the sugar, but it will etch and eventually dissolve your teeth. If you take a chicken bone or something, put it in Coke, it'll just turn it into rubber. So reactions going on there that because of the acidic nature of those materials. When you go the other way, the bases, you know that Clorox and bleach is a pretty strong base. You can pour bleach on a pair of jeans or something and take all the color out. If you don't wash it out, it'll actually eat the jeans. It'll break down the fibers, and you'll have nothing left but lint. People sometimes put bleach in their hair or something to change the color. Well, you can change the color. You can actually change your hair, right? All your hair will fall out if you put too much, and if you leave it in there too long. It's dangerous stuff. There are other bases down here that are even stronger, sodium hydroxide and some of those, but these are kind of everyday things. Ammonia is a base. It's about 11.5. Stomach antacid, somewhere around 8.7 or something, I'm guessing. Baking soda is a base. The old time remedy, if you didn't have antacid but you had an upset stomach, you could mix up some baking soda and water and drink it. It had that basic property. An upset stomach comes from too much acid, so if you put some base, it neutralizes, meets in the middle here again. So the pH scale is kind of nice. It stands for the potential of hydrogen, which is kind of a funny title, but that's the way it works. You got more hydronium ions, you go this way. If you got more hydroxide ions, it goes to the basic side. Both acids and bases can be dangerous. You need to be careful with both. Another name for basic is alkaline. So some may see alkaline batteries or something, and they have a base in them. Okay, very good. Thank you.